Everybody, welcome to the stream. All right, so what are we gonna do today? So I've got this Arduino starter kit for center class. I have this sick idea that I want a light in my room to start blasting like light throughout my room, just like a disco light or whatever, just like looped around my room. And then I want Twitch chat to be able to actually control the colors and like speed, and maybe I could actually make it based on the music that's playing or something like that. And I want to do that with the Arduino, just so I can learn some basic electronics, because I haven't ever done this. It's good that I just have like the entire setup like ready, because you can get like Arduino electronics from like, or you can get like basic parts for the Arduino like pretty much everywhere on the internet, and they're way cheaper than this set. But the thing is because I don't have any experience with hardware, buying that is kind of risky, because if you buy a set that has broken parts already in it, because it's like really sensitive stuff, then I don't know if it's my fault or if it's the device's fault. So I wanted to start off with making sure that I buy something that is 100% like working. It's probably a little easy for me because I've got a little bit of experience like in programming, so I think like the programming part is going to be super easy, but the hardware part is probably going to be pretty difficult. So in the box, there's obviously the Arduino itself, a breadboard. You get the breadboard with you get the liquid crystal display, so we can show stuff on this screen based on like whatever the fuck you do with it. Then you've got the USB cable just to connect it to your power. I don't know what the fuck this is. This is like a wooden board. I don't know what the deal with this is. Then you have the electronical components. So these are the LEDs, and like it looks like LEDs and some other bullshit that I don't know about. Like I don't know anything about like hardware at all. This is the rotors. So they come with rotors and a motor, that you can see right here. Motor CC servo motor. And then I think this is the part that is actually just the paper part that you can use for all the projects that you have. So I think this is probably to spin around something using that servo motor. And that's it. So that's pretty much all that comes in the box. Okay, so I think we're gonna start off with looking at the book and just reading out what the fuck is in there and see how the fuck we're gonna do this. So they're gonna introduce me to all the parts. This basically explains exactly what the purpose of every part of this thing is, but I think I will read this as we go. I think that makes more sense than just to go through and figure out what the fuck everything is. All right, setting up. Before you start controlling the world around you, you will need to download the IDE to program your board. Oh, okay, let's do that. So it tells me that I have to download the IDE. I have the IDE set up. All right, let's continue checking what the fuck we have to do. So, things you need to supply. A 9-volt battery, a small light source like a flashlight, conductive material like aluminum foil or copper mesh, colored paper, scissors, an old CD or DVD, tape and glue, a box that you can make holes into, basic tools like a screwdriver, and I need a soldering iron and solder. What? I don't have that. Okay, not for now though. Necessarily only in project 15. There's 15 projects. Holy guacamole, dude. Alright, that's gonna be cool. Now that you installed the Arduino IDE, make sure your computer can talk to the board. It's time to make sure you can upload a program. Alright, beautiful. So we got this thing. Let's take out the Arduino itself. Would you look at that? That's the tiny Arduino that we have. All right, let's connect this bad boy. Does it not go further than this? All right, it's on. Lights blinking. Okay, so what do we do now? Look for the Arduino device under the category Other Devices. All right, this is the blink example. Turns an LED on for 1 second, then turn it off for 1 second repeatedly. Choose the serial port that your Arduino is connected to from the tool's serial port. Okay, I think this is good. And then you say upload. Let's hope it doesn't explode. Exactly. Oh, look at that, it's working. I think it was uploading. Is that the LED blink? Change the delay timer by changing the number in the parentheses to 100. We're gonna change it. To be 100, a delay of 100. So the loop is just gonna loop over and over and over and over and over. And then we digital write LED built in to be high, which is probably turning on in the highest voltage level. That's what it says. Then delay for 100 milliseconds, then write it again to be low, and then delay 100, and then it starts up from the top again. So this thing will run constantly, back and forth, start to finish, every single time. Setup is only probably run once, I suppose. All right, let's do that. Let's hit upload. See that this thing will start to blink. And you can see it starts blinking faster now, so it is working. You can see it's like a 100 millisecond interval now, turning off and on. All right, so what we're gonna do is you'll make a small circuit with some switches, an LED, and a resistor. Discover basic electrical theory, how a breadboard works, components in series and parallel. So that's what we're gonna be learning today. So electricity is a type of energy, much like heat, gravity, or light. Electrical energy flows through conductors like wire. You can convert electrical energy into other forms of energy to do something interesting, like turn on a light or make some noise out of a speaker. The components you might use to do this, like speakers or light bulbs, are electrical transducers. Okay, so we've learned two things already. Electrical energy flows through conductors, first thing. Second thing is electrical transducers. Transducers change other types of energy into electrical energy and vice versa. I don't know what that means, but I think we'll figure it out. Things that convert other forms of energy into electrical energy are often called sensors. And things that convert electrical energy into other forms of energy are sometimes called actuators. All right, I have no idea what all that means, but I think we'll figure that out. You will be building circuits to move electricity through different components. Circuits are closed loops of wire with a power source, like a battery, and something to do something useful with the energy, called a load. In a circuit, electricity flows from a point of higher potential energy to a point of lower potential energy. Yeah, so there's like plus and minus. So higher potential energy is plus, lower potential energy is minus. In the circuits you're building, electricity only flows in one direction. This type of circuit is called direct current, or DC. In alternating current circuits, electricity changes its direction 50 or 60 times a second, depending on where you live. It's the type of electricity that comes from the wall socket. Produces means it's a device that translates one form of energy to another form of energy. A motor uses electrical energy and converts it to mechanical energy. Ah, I see. That makes sense. Yeah. I see. So which part is the transducer? Oh, that's the motor. So the motor, in this case, is the transducer in order to convert electrical energy into mechanical energy. Right. So it takes energy, like electrical energy, to power and create mechanical energy. That makes sense. Cool, thanks. That makes a lot of sense. There are a few terms you should be familiar with when working with electrical circuits. Current, measured in amps, is the amount of electrical charge flowing past a specific point in your circuit. Voltage, measured in volts, is the difference in energy between one point in a circuit and another. And finally, resistance, measured in ohms, with the symbol ohm, yeah, is how much a component resists the flow of electrical energy. Okay, I don't know what that means, but we'll see. This is really interesting to me, guys. Like, this is probably like not primary school, like high school stuff everybody should learn. And I've seen like amps and voltage and all that shit, and I've learned the formulas, but you know, that's like a very long time ago. And when you're older, you start to like understand what certain things mean and what they apply to. So like learning it in this form, I think makes a lot of sense. I think people should actually be doing this in high school. Everybody should just get an Arduino, and you learn like voltages and amps and like resistance and all that shit just through working with an Arduino. I think that makes a lot of sense. Okay, so we're talking about resistance still. So resistance is how much a component resists the flow of electrical energy. One way to imagine this is to think about a rock slide going down a cliff. The higher the cliff, the more energy the rock will have when they hit the bottom. The height of the cliff is like this voltage in a circuit. The higher the voltage at the energy source, the more energy you have to use. The more rocks you have, the more energy is being carried down the cliff. The number of rocks is like the current in an electrical circuit. The rocks go through bushes on the side of the cliff, losing some energy in the process. The energy is used to crush the bushes. The bushes are like resistors in the circuit, often offering resistance to the electrical flow and converting it to other forms of energy. Ah, that makes sense. The current are the rocks. The voltage is the mountain, or the rocks, the cliff. And then the resistance is whatever the fuck. It basically takes the current and uses its energy for something else, right? A couple things about circuits. So there needs to be a complete path from energy source to the point of least energy to make a circuit. Yeah, that makes sense. So to make sure that the energy flows through, right, that there's current flowing through, it needs to go somewhere, right? It needs to, in order to flow, it needs to flow from one point to another. And then in between that flow, we can use that energy, I suppose, right? I think that's a way to look at it. If there's no path for the energy to travel, the circuit won't work. All the electrical energy gets used up in a circuit by the components in it. Each component converts some of the energy into another form of energy. By adding components to the flow, we basically reduce the current, right? Because there's only flowing so much energy through the system, like by the amount of voltage that we give it, that all your components in between are using up all that current, right? I hope that's correct. I hope that I look at that the correct way, but continue. Each component converts some of the energy into another form of energy. In any circuit, all of the voltage is converted to another form of energy. Light, heat, sound, etc. Is that a rule? Otherwise, it's a waste of energy, I suppose, or something? Oh, I guess. Okay, no, I understand. So that's what the resistors are on a circuit board. These are just to basically make sure that there's no current left. There's no voltage left that's running through the circuit. So you have a circuit board and you push through a bunch of voltage. And then if your components don't use all of that voltage, you would need to place resistors there in order to make sure that it's like collected, so to speak. I hope I understand that correctly, but I think that makes a little bit of sense. The flow of a current at a specific point in the circuit will always be the same coming in and going out. The rocks in that story are electrons that flow through a wire. A battery pushes the electrons. A resistor resists against the movement of the electrons. The electrons have to fight to get through the resistors. The friction between resistor and electrons is given off as heat. What remains are electrons that come out of the resistor. If you have a connection that connects power and ground together with no resistance, you will cause a short circuit. And current will try to follow that path. In a short circuit, the power source and wires convert the electrical energy into light and heat, usually as sparks or an explosion. If you've ever shorted out a battery and seen sparks, you know how dangerous a short circuit can be. So what's a breadboard? Oh, this has been the longest question of my life. I've always looked at a breadboard and I didn't understand shit of it. Okay, so a breadboard is the primary place you will be building circuits. The one that comes in your kit is solderless, so named because you don't have to solder anything together. Sort of like Lego in an electronical form. All right, we've got the one here. The horizontal and vertical rows of a breadboard, as shown in Figure 3, carry electricity through thin metal connectors run under the plastic with holes. All right, let's open it up. Let's see what the fuck this looks like. Oh my god, this is like really tiny stuff. What the fuck? So in is a plastic bag with tiny, like, metal pipes in between, I think. Oh my god, what is this? There's so much shit in this. All right, this is the plastic one, and you cannot see anything. What is like actually inside here? The breadboard. Yay. You can see like the numbers and everything on there. 1 to 3 A B C D. And then I think you can reference these places through code. I think. All right, cool. And then we've got a bunch of bags and like some longer connection cables. So I guess this is to make the circuit, right? This is to say like, let the energy flow through these tiny things from one point to another, as long as they go from plus to minus. The middle row breaks the connection between the two sides of the board. Yeah, that makes sense. This is a power bus. The sides of it are the power bus. So this one and this one. This row. These two rows. And it has plus and minus on them. The 5 holes in each horizontal row are connected electrically through metal strips inside the breadboard. So the middle rows, these ones, like these two, are, and then every row, so like the ones with the numbers, and then it's like every row, so it goes all the way up, is connected electrically through metal strips. Vertical strips that run the length of the breadboard are electrically connected. The strips are usually used for power and ground connections. Right. So that's what I said. So the plus and minus on the side are used for power. The ones in the middle are basically used to create the circuit, I suppose. Throughout these projects, you will see 2 views of circuits. One breadboard view, like in figure 5, and then one view of your kit. So it shows me here the breadboard and then the Arduino itself, because there's like connectors on here as well. Here's a bunch of them and here's a bunch of them. We're taking way longer, but I'm completely fine. I'm learning so much already. It's insane. All right, so now we're gonna actually get down to it. We're gonna talk about our first components. So they're talking about an LED, a resistor, and a switch. Say the LED, the resistor, and the switch. So this is the button, this is, the resistor, and then this is the LED. An LED is a component that converts electrical energy into light energy. LEDs are polarized components, which means that they only allow electricity to flow through them in one direction. The longer lag on an LED is called an anode. All right, let's get one of those LEDs out. An LED that we have right here. An LED. It's not like we don't want to break it or anything. It has a plus and a minus. How do you know which one is which one? It has a cathode, which is the minus, and an anode, which is the plus. The longer lag on an LED is the anode. So the longer lag of this one is the plus, and then the smaller lag is the minus. Okay, so that's how you know. The short lag is a cathode and will connect to the ground. So that's the minus. When voltage is applied to the anode of the LED, and the cathode is connected to the ground, the LED emits light because it has energy flowing through them, right? Energy will find, it goes from plus to minus. So if you are in between that with a component, energy will flow through and it will use that energy in order to. A resistor is a component that resists the flow of electrical energy. See the components list for an explanation on colored stripes on the side. It converts some of the electrical energy into heat. If you put a resistor in series with a component like an LED, the resistor will use up some of the electrical energy and the LED will receive less energy as a result. So that's what I meant, right? So the LED will use some of the energy, but depending on how much voltage you flow through the system, through the circuit, it might be too much, right? So what a resistor does is it takes some of that energy and converts it into heat instead. So you can blast through a fuck ton of voltage and then have a fuck ton of resistors in between and still let your LED not like blow up basically by too much voltage flowing through the LED because you have so many like resistors in place. But you would rather not waste that amount of energy with blasting a lot of voltage, because both it will create a lot of heat with the resistors and then also having the the wasted voltage, right? Because you're not using the voltages, it's literally just going up in heat, basically. I think that makes sense. I think we're onto something here. I hope I get that correctly, because I'm telling myself that this is the right way, but I don't know. If you put a resistor in series with a component like an LED, the resistor will use the blah, blah, blah. This allows you to supply components with the amount of energy they need. Yeah. This allows your to take the amount of energy they need. So you need to know all your components, like how much voltage they need, and then know exactly how many resistors you need to make sure in order to not blow up your component. Without the resistor, the LED would be brighter for a few moments and then quickly burn out. Yeah, exactly. A switch interrupts the flow of electricity. Breaking the circuit when open, when a switch is closed, it will complete a circuit. There are many types of switches. I assume that you can basically tell it, like, it's basically a guide, right? Like, okay, how I imagine a switch is just, it flows energy through. So it is basically just closing off and just letting it pass. And then you can tell it like to open up in a different part of the circuit. So normally it would just loop like this. And then you have another branch like this with an LED here. Your switch would just, when it's on, it will just guide the energy towards that other branch and then close up the signal, probably back to the switch. And if it's closed, it will just let it flow through in this circuit. I think that's probably what it is, but I have no idea. So let's read. When the switch is closed, it will complete a circuit. There are many types of switches. The ones in a kit are called momentary switches or push buttons because they are only closed when pressure applied. Okay, so only when you, like train tracks. Yeah, exactly. So this one is only if you push it, it will open up the circuit. So I guess that's perfect for if you want to give something power when you have your finger on it. Probably a fuck ton of resistors in here. Is this a resistor? Isn't this a resistor? You see these on your motherboard as well. Oh, these are resistors. You see them now. Oh my god, there's so much shit in here, man. I don't even know what this is. Like a brush. Alright, here are the resistors. Holy fucking moly. That's quite a bit of resistors right there. You need to fuck ton of them sometimes. I assume that some of them are more resistant than the others. I assume. So we got this line around here. I like this line around here. Yeah, reading the color codes on them. Oh, great. I think I have the color codes in the book, so I think we're good. Your first interactive circuit using a switch, a resistor, and an LED. Arduino is just the power source for this circuit. In later projects, you will connect its input and output pins to control more complex circuits. So we're only using the Arduino for now. So no breadboard, I suppose. Oh no, we're doing it. Oh my god, I'm already scared. So 5-volt at the top going into the system, then 220 ohm of resistors, push button, LED, and then back to ground. Okay, now we're gonna use the Arduino in this project, but only as a power source. Plug it into a USB port or a 9-volt battery. The Arduino will provide 5 volts between its 5-volt pin and its ground pin. Yeah, so that's what I showed on the image, right? If your Arduino is connected to the battery power, unplug it before building the circuit. So connect the red wire to the 5-volt pin on the Arduino. Motherfucker right here. We're gonna stick this into the 5-volt on the Arduino. Gotcha. And the black one goes into ground. So there's a couple of ground pins on the thing already. You see the ground ones? The white strip next to the red wire here? It says ground. So we're gonna stick that in with the black cable, which is gonna be our grounding cable. I suppose that there's no difference between these cables. It's just the color. So just so you know, probably like convention saying like, okay, the black ones are always, you know, the minus part of the circuit. All right, so then we connect the black one to the minus and then the red one to the plus. It's helpful to keep your wire colors consistent. Red for power, black for ground. See, that's what I said. It's the same cable, it's just convention. At least for your board. At least you have to know which one is which one. Now that you have power on your board, place the switch across the center of the board. Okay, let's just do exactly what they do and then just figure out why that is later. Is there anything that I need to know about this one? All right, that one's in. I don't know how hard you have to press those things, but let's try. So it doesn't matter where I place it in theory, as long as I connect the wires correctly. All right, next. Use a 220 ohm resistor to connect the power to the one side of the switch. All right, let's get one of those resistors. Do you take them out of this fucking thing? Probably, right? How do I know which one it is? Your kit may have a mix of 4 or 5 band resistors. Use the illustration on the side to check the right one for this project. Look at page 41 for a detailed explanation of the color codes of the resistor. On the other side of the switch, connect the anode. Yeah, okay. So let's first go to page 41. There we go. How to read resistor color codes. Resistor values are marked using colored bands. According to the code developed in the 1920s, when it was difficult to write numbers on such tiny objects, each color corresponds to a number like you see in the table down below. Each resistor... Oh, that's actually a cool history thing. It makes sense though. It was kind of difficult to write the number on such a small object. Each resistor has either 4 or 5 bands. In the 4-band type, the first 2 bands indicate the first 2 digits of the value, while the third one indicates the number of zeros that follow. Technically, it represents the power of 10. The last band specifies the tolerance. In the example below, gold indicates that the resistor value can be 10k ohm plus or minus 5%. Each resistor has either 4 or 5 bands. In the 4-band type, the first 2 bands indicate the first 2 digits of the value. And then you have like the color codes right here. So this, I guess you read it like this. This being 1, and then this being 0. So that's 10. 10. And then the 3rd band indicates the numbers of zeros that follow. So it started with the two numbers, which is 1 and 0. So that's 10. And then the amount of zeros that follow. So then yellow, which is 3. So that's then 10,000. That makes sense. And then the last band specifies the tolerance. In example below, gold indicates that the resistor value can be 10k plus or minus 5%. So you have gold, silver, red, like you have dark red, red, gold, and silver. Why is silver more percentage tolerance? Because it's less precise. Break it out. 1 band is 1 color, so the first number is 2. So 2 is what color? 2 is red. Do the same for the second. So if I were to be 220, I need to find 2, 2. And then is like... And then a 1. Which is a purple. Yep. So 2, 2, 1. And then whatever the fuck comes after it, which is gold in this case. Okay, that makes sense. 1, 0. Yeah. Should be brown. Well, I don't know. It's like... It's... I don't know. Is that brown? Maybe it's brown. Yeah, that's brown. Not a 7. Purple is strictly 7. I thought it looked like a purple, but that's might be the lighting of my room. See, it's like red and it's brown. Yeah, it's kind of brown. It looks on stream, it looks brown too. But I get what it is. Because if it were to be, if it were to be the other one with a 7, that would mean that I'm resisting 22 with 7 zeros, and then basically there would be no fucking power left. And then my resistor would be chilling. My resistor would basically block off everything, and then would it short circuit because it doesn't go through, so it never reaches the minus? What would happen? What would happen, chat? If my system does not actually get to the end, so the resistor is blocking off all the energy, it will just create heat, right? So all the energy converted that you're blasting through the system will just create heat because the resistor will block it off and it will create heat. What will happen though? Is there just going to be constant voltage blasting through, heating up the resistor? All right, let's find the resistor first. So I have a bunch of these. And I need to find... This is... Which way do you read it? Okay, yeah. I guess you have the golden side, so you only have gold, silver, red, and brown, right? To start off with. And the distance between the last one and the first three are like way closer to each other. So that makes sense. Okay, so I've got... I need red, brown, and then whatever. God, it's so hard to see. What the fuck? Am I fucking blind or what? Oh my god, I bent the fucking thing. Oh god. Get out! This one side is stuck. Pissing me off. What the heck? Oh my god, this one was so stuck. Alright, so I bent the entire thing. That's fine though. Alright, one side is a little bit fucked up, but we got him. Alright, one more verification. Just to be sure that I get it. If I look at the colors, this one should be red, which means 2, and then 0, and then brown, which is 1%. Correct? Are we good? Just so that I understand it correctly. Red, black. That's 220. Perfect. All right, so where are we at? Okay. So let's go back. Sorry, we're a little slow, guys, but it's all right. I'm learning a fuck ton, so I'm happy. So we have to add the power from the left side plus to anywhere on this row, right? On this horizontal row here. So having the plus here, this side, and then the minus one row below. I don't know if that makes any difference. Then as long as it hits this row right here, so this first row of this switch, we should be fine, right? So I can put it anywhere on that row, but let's just put it exactly where they put it. Let's bend the fucking sides a little bit. And then it should be on that row, like the horizontal row, basically. On number 8. So on number 8, we have to move it from plus to number 8. Somewhere on that row. It doesn't matter where, I think. So let's put it down. All right. Let's hope it's in correctly, but we'll see. Okay, so now I create a circuit using those circuit thingies. This ones. They have like smaller ones and bigger ones. I don't think it really matters. So let's move it from 10 down. How far do you have to push it down? All right, so that's in. So we're basically moving the resistor here from plus. So there's plus current going in, right? And then it goes through this switch. And then my plus needs to be on the starter side, I would say. So my longer one should be on the start end. Is that correct? That one should be on the group. On the group of yellow, so where yellow comes in. So where the out of the switch goes. We connected a circuit, the yellow one, to fucking number, I don't know, 14. Then on the same horizontal 14, we also added the start of LED green, which is the plus. And then where the fuck, what group it goes out, we have to go back to minus. Right? That's how we do it. So this bad boy now, it's just group 15. We now have to connect it to go back, which we can use any cable for, to anywhere minus. But they used it a group lower. We can go to minus. I'm just doing the same thing as in the book, which is one lower. Do you have to push it all the way down, or can you just move it up like this? Does it like connect all the way, or do I have to push it down? Because this one is like pushed down all the way. Do you have to push it all the way, or does it not matter? What's up, Pizza Hopper? How's it going? As long as it touches the internal contacts. Okay. Yeah, I think we should be fine here. So in theory, I don't even need the circuit in between, right? In theory, I could also just add the LED directly to the group of the switch, right? So I could also just add the long leg there and then not like have them right next to each other. But it's nice that we're learning, you know, like using the actual connectors in between. Connect the anode long leg with a wire connected from the cathode short leg of the LED to ground. When you're ready, plug the USB cable in the Arduino. Once everything is good to go, press the button and you should see the LED light up. All right, let's connect it, boys. We have power. Oh! Boys, lads. We're doing it. We're doing it. We've made our first thing. Hell yeah, boys. We've done it.